Morning. First of all, thank you very much for Darius and company for the kind invitation. I am Alberto Rodriguez. I came from a medium-sized university in the southeast of Spain, a town called Elche. The university is called Miguel Hernández University. Inside the university we have the School of Engineering, where we talk most of the engineering studies we have. I've been working there for 17 years almost now, always in this School of Engineering. Now I am also Deputy for International Relations, but all these 17 years I've been working in the field of signal processing, mostly in the field of time-to-frequency analysis. First I thought, and mostly apply it to ultrasonic signals. Problem is that last year's two keynote speakers, they talk about ultrasonics, so I thought it was going to be too much ultrasound for a conference. So I also have been working in the field of autonomous vehicles. It has been for the last 3 years, very small project for an American-German company. I had a former student who was working in this company, who is still working in this company. Actually, he got promoted now, and he's living in the United States. And they manufacture, well, actually it's here, they manufacture power steering systems, okay, just for any sort of cars, Volkswagen, Opel, whatever. And they were working with a small sensor, and they had some problems, so I started working with them, just to do the signal processing of these signals and to achieve the problems they have. We will see now. Well, we will not see, because unfortunately it is protected under non-disclosure agreement, so I cannot tell everything, just a very small thing. From the surface it's going to be just 5 minutes, and then I will talk to you about what really is autonomous driving and the challenges of autonomous driving, because I have started working in this field for very short time, but I think it's really exciting, and I think it's a big opportunity for electronic engineers, because there is a lot of money involved in this part. So I think you will maybe not enjoy it, but you will find it interesting. So what was the problem here? There is a small sensor. It is a it's electromagnetic sensor. It has to detect if the driver is doing some torque in the power system, in the steering wheel, then to help the system with an electric motor. The problem is that they want to develop an automatic system for the auto calibration of the offset of the sensor with time, but for this they have to be sure that nobody was acting on the steer, touching the wheel. Okay, but they have to do it themselves without the help of any other sensor, because this is manufacturing. They were manufacturing only this part of the car, and they sell to the manufacturer of the car. So they don't want to ask to the manufacturer for an extra sensor in the wheel. They have to do it themselves. So the idea was to use this small sensor. It's not very easy, because the sensor is quite simple. It is extremely cheap, extremely simple. It is only one part of the whole system. It is a few dollars, and the power of the sensor is very low. I mean, it is working, sampling frequency is about 112 Hz. And the processor is quite simple. So it was developed only for the management of the motor, not to acquire or process any signal. So the problem is that they have to detect if somebody was touching the wheel. So there are two events, two hypotheses: hands-on or hands-off. It's not only hands, whatever is touching the wheel. The problem is that these signals are quite low frequency. So imagine somebody is touching the wheel. You can be touching the wheel just doing nothing. This is very low frequency, okay, regarding to the movement of the wheel. So it is almost zero. It's not zero, but it is almost zero frequency. And even if you move the wheel, it would be very stupid to do it very fast, but even if you do it, okay, it's going to be low frequency. Problem is that for that very short or very simple processor with very short windows, it is extremely difficult to measure things with very low, just touching the wheel, very low power on the system, and very low frequency. So we had to develop some way to do it. Actually, they had an idea. They had already made something. They had old system in which they introduce an artificial vibration in the motor. Okay, so they were put into some frequency. I cannot tell you, but they were the motor was vibrating very. It's not high frequency. Okay, it's between 15 and 50 hertz. Okay, but it is vibrating with a very low power, so you don't feel it. Well, actually, the car is very low, but it will produce an effect in the signal. Okay, so this is more or less the signal we have here. Nobody's touching the wheel. This is a simulation, okay, because I cannot show real data, and this is not, but more or less is, no, actually this signal is real, okay, this is real signal. So this is the signal with the vibration introduced, okay, and here we have the offset, and then somebody here is touching the wheel, okay. This is actually made artificially to see the signal, but normally it is something like this, very close to this level. So it is quite difficult to get this with the simple device. So this compared to this, which was the original, this is an spectrogram, okay, this is frequency, this is time, so around 30 hertz, this is the artificial vibration, this is the low frequency hands-on event. There are some changes here, but for the device it's very difficult to measure them. And actually, as I told you, this has been artificially made too big. But when they are very small, it is very difficult to sense it. So this is what we have. So we started from making the simple power spectral analysis, just doing a spectrogram, okay, this STFT, very simple, spectral analysis with time. But then what we do is, again, doing another STFT of the STFT. So it is a double power spectral analysis, okay, it is quite simple, but it works very well. At the end, what you have is more or less this, okay, I have resumed briefly because, as I told you, I cannot tell you everything. Otherwise, I will have to kill you, and there is many people here. So the idea is that after doing this double power spectral analysis, you have something like this. And if you see, there are many factors like those. Those are sync-like functions in frequency, okay? And you know sync-like functions. They have a main lobe. It is quite simple. It's a main lobe with some zeros, okay? So the idea is something like this. It is a simple function which appears in when you are developing the mathematics of the function. And it is funny because you can play, if you play with the vibration you introduce into the system and with the size of the window, you can put the zeros wherever you want. And as you are doing a double spectral analysis, you are modulating the signal artificially. So at the end, we were passing from this to this. So this was much easier for the system. So it only has to calculate the power at a single frequency in the double analysis using very small windows in time, okay? Less than 12 samples. So it was able to produce fast results, very accurate. Actually, it was, I can tell you that it was just touching like this, the hand wheel, it was able to detect it. So that was it was very good. Actually, not even with the hand, whatever you put on the hand wheel, it detects. But the good thing is that it was very easy. You just have to calculate at a single frequency, okay, and it is fast and easy. And this is real data. What we have, well, this is the result of the double frequency analysis. This is frequency, and this is frequency again. So this is hands-off event, and this is hands-on event. As you see, the peak is quite strong here. Okay, when it appears, it is very easy to isolate it, and it's very easy to calculate. So it worked very well. And they have patented it, not this particular thing, okay, there is many things behind that, more mathematics, but it works. And the good thing is that now we have extended the project. Now it is stopped because they are very busy with a new project in real mechanics, but the idea now is to use this sort of sensor, actually, to detect whether if the car is driving in which sort of pavement, if it is asphalt or gravel or there are blocks. So the car can deal with it and adapt itself to this environment, okay? But the important thing is that this sensor, it comes from an old design, okay? This sensor, and this whatever system they are using, wasn't thought to be used in any sort of autonomous vehicle. But now they are developing new software into these small devices so they can add some new value to their product. Because nowadays competition is very hard. They are the third world producers of these sort of systems, and the competition is very high. So the more they add to the system, the better. So once I finish with this small project, I think I have taken too much time. So maybe it will be a good idea, because as we have problems with the speakers, maybe it's good. So the second part is going to be, I just want to talk to you about autonomous vehicles, because I have to start from zero, and I have to learn a few things. It's going to be very basic, just basic ideas, but you will see where are the problems and where are the challenges, okay? So first thing is that, of course, I want to stress that it's a very important field. So there are many institutions putting money on this and taking care of this. There are many laws. Now, actually, the European Union, there is a declaration of the European Union telling all the states involved which laws should they do and how many money and in what should they invest. And there are many European projects, many private projects from companies, car manufacturers, electronic manufacturers, communications companies that you will see. So it is really important field. Then what is autonomous vehicle? This is what everybody thinks that the reality of autonomous vehicles. Okay, no. Where is it? Here. So, of course, it's not real, okay, and this is not what we are now. This is made by some movie makers, and this is not real, and there are so many things that go wrong in this video. It's really scary, okay? I wouldn't know where to start with, but this is what we would like to have. Okay, this is the ideal system. It would be impossible with humans and robots all together, but okay, it will be ideal. So we will start. What did we come from? Okay, not historical far away, but shorter term, where it really started to become a reality. And it was in 2004 where the Defense Advanced Research Projects Agency from the United States launched the first DARPA challenge in 2004. It was a challenge for university companies and research areas. For autonomous cars, they have to drive in Mojave Desert in the United States 100 miles with obstacles, taking routes in real time, and the price was $1 million, and no team finished, okay? You see the cars, they look like funny things like the 70s movies. They are very interesting. The second one, it was next year, and again in Mojave Desert, 100 miles with objects. They have to take decisions. Now the price was $2 million. Now 4 teams finished. Second one led by Chris Urmson. This was later he was the manager of Google Car. And you see now the differences, okay? So from here to here, there is a big difference. It's only 1 year, okay? That's because manufacturers started to understand that it was going to be interesting, and also universities, and they started to put a lot of money. And this was the last one in the year 2007. The third one, it was in urban environment, okay, inside not a city, but inside an urban environment closed for this thing. Price was €2 million, $2 million. This time 6 teams finished, but of course the cars were very, very different. Now they have LiDAR, they have radar, the CPU was really big. But the most interesting thing is this. If you see the six who finished, they were Carnegie Mellon University, Stanford, Virginia Tech, MIT, University of Pennsylvania, and Cornell University. Those 6 were the 6 who finished, and they are the best universities in the world, technological. So you see how important it is and what a challenge is this. The 6th one, the 7th, who didn't finish, it was a German, non-American, so it was at least European. Then another American, and then another European. And again, very interesting, you see the sponsors of the teams. This is Carnegie Mellon, the sponsors General Motors, Intel, Google. Okay, it was 2007. And for Stanford, it was Volkswagen, Intel, Google again. So it is starting to get serious, okay? The next big step, it was when Google decided he wanted to play the game. So in 2012, they make one state to change the law, so they were allowed to drive in real streets, to start collecting data and to actually probably also to make noise and to show that they can do it. But they did it. So in 2014, the first autonomous car, this was the small Waymo. It was this small ugly egg with no steering nor pedals. It was really a robot. Okay, but then they changed to supervised vehicles because they understood that it was more safe, and they could. And with this change, they can spread the driving in other states in the United States. In 2017, they partnership with Intel, and this year they partnership with Jaguar, and they have ordered 20,000 e-Pace Jaguar. So it is serious again. The other actor which is making a lot of noise and who has really started also all this is Tesla, because they were the first who put an autopilot, they call it, but it is not autopiloting. It's not an autonomous car. It is a car with a very clever assistant driver system, okay? But it is not able to drive. It is only helping the driver, as we will see later. But the good thing is that they started the thing. So everybody now is jealous because they are selling a lot of cars. They have a very good image, so everybody wants to do it. And of course, there are more manufacturers. Audi and Mercedes are selling cars now with autopilot in traffic jams. Okay, in very specific situations they can do autopiloting. Of course, auto parking cars. This is very usual. Auto braking system. This is very usual nowadays. Platooning is going to be a next step. They are going to do it very soon. Actually, real testing. For a long time, and it is not new. You know, platooning is when there is one vehicle on the front, which is actually driven by somebody, okay? And then the rest of the vehicles are behind him, very close. So the idea is that they reduce the air resistance, which is good for trucks, so the consumption of fuel is very low, reduce congestion, they shorten commutes, vehicles can be partially unattended, and there are fewer traffic collisions. They are not robots, there is somebody behind the wheel here, but they can be resting, for example, or they can be just talking with the mobile or whatever. But this is it, and this is real. This is real. Scania testing. Mercedes is going to deliver one, they say, in 2020, and Tesla is producing as well. They have some experiments with this, and they have made a lot of noise, but we will see. And the problem is that with all this came the dark side, which is also very important. The problem is that if you put, because they are robots, sort of robots, if you put robots which are learning, because they are learning now, with real people, which are highly unpredictable, the results are not very good. Okay, so there is a dark side with it. We will see why this happen. These accidents happens if we have time, but it helps us realize that there is a need to have a common standard between all manufacturers, researchers, between legislators in the countries and users about what it is autonomous driving. Okay, so I can choose a car which has this level of autonomy, okay, or this other one, and this one can drive in this sort of environment, and this one cannot. Okay. So there are some certain rules in different countries, and all of them are based on this CAA G3016 taxonomy and definitions for terms related to on-road motor vehicle automated driving system. Those are the 6 levels. It is level 0 and level 1, 2, 3, 4, 5. And they all depend on the attention of the driver in the system. Okay? There are 2 key factors, which is longitudinal control, okay, who is accelerating and braking, and lateral control, who is in control of the steering wheel, okay? And according to this, there are several different levels. So we have level 0, which is only warnings. There is no control at all. The car is not controlling anything, but it is giving a lot of warnings, so helping the driver, which is assisting the driver. It is telling him you are out of line, so something blinks, some noise appears, and the driver has to move. Or there is an obstacle, so you have to brake or you have to push the pedal. Okay, depends, but it is not autonomous at all. It is not. It is the driver one side and the car in the other. This is level 1, which is called hands-on. Okay, in this one, the car is controlling or the longitudinal control or the lateral control, but not both. Okay, there are already cars like this in the market. So, for example, Tesla. Well, Tesla is actually level 2, but there are not only Tesla, there are more cars. This one, for example, you can set the speed, okay, and it will not. It's not auto cruise. It will hold the speed, and if there is an obstacle, like another car, it will push down automatically. You don't have to do anything. And when the obstacle gets off or it goes faster, it will again push up. So you don't have to do it. Then you have lateral control, which is the car will stay inside the lines. If there is a curve, the car will go in the curve. Okay, it will do it automatically, but not both things at the same time. Okay, so this is level 1. Level 2, which is Tesla, sort of autopilot. It shouldn't be autopilot because it is misleading people to run things, because it is not piloting for you. It is helping you in the two controls. But for example, it have control of the longitudinal and lateral movement. But for example, it cannot overtake. Okay, if it is going in a road and there is an obstacle, it will brake, or maybe it will move in an emergency movement if there is no obstacle in the left, but it will not overtake the obstacle, and it will not go from point A to point B completely. Only in specific inside parkings or in very short distances, but you cannot rely on the system. Actually, level 2. It's a hands-off, not really hands-off. It should be called hands-off partially, because in less than 3 seconds, between 1 and 3 seconds, according to a standard, you have to take control of the wheel. Okay? So in 1 second, a lot of things can happen. So actually, for example, in United Kingdom, you have to be with your hands on the wheel. It is mandatory, even for Tesla. So that's why people who is buying a Tesla, they think they have an autonomous car and they relax, but it is far from it. And accidents happen. Okay. We have level 3. Level 3 is ease off. It means that you can relax for longer period of time. Okay, you can for 15 seconds according to the standard. So you can relax, you can take your A off, but as you see, the driver has to be close to the control and has to be ready to take control in 15 seconds, 10 to 15 seconds. This is, for example, inside parking lots, platooning, of course. So once I get into the motorway or the road, it is going to be platooning, and it do it autonomously. Once I want to get out of the platoon, then I take control and go out. Okay, or I can take the phone call, or I can test a message. Then it comes level 4. Level 4, the car still has a hand wheel over there. Okay, but you can relax completely from driving. Okay. You don't need to attend the system because the car can deal with everything inside specific environments. For example, motorways. So you say, I want to go from Palanga to Kaunas, and it will go alone, but only if the roads are ready for this. It means some antennas, some system recognition, cars are talking together, not autonomous car maybe are not allowed to get into this road, so it is only under specific environments. Okay, there are no real cars level 4, not in the streets. Level 3, partially. For example, I would say that Tesla or maybe Audi and Mercedes, for traffic jam assistance, it could be considered as level 3, but only under very specific circumstances. But really not, they are level 2. So there are level 2 cars, Tesla, Audi, Mercedes, top level Audi and Mercedes, the new one. And then we have level 3, no commercial car, level 4, no commercial car, and level 5, which is driver optional. Okay, you don't even need the hand wheel. They are producing these cars because it is good for them for testing, and in some states it is mandatory, but it wouldn't be needed. They are robotic cars actually. Okay, and there are not real cars like those, because Waymo and Uber, they are only testing now. Okay, you cannot buy or you cannot get an Uber. Well, you can, but maybe it's a bit dangerous. We have seen. Take a Uber car or Google car and saying, I want to go to this place, and actually now there is a driver inside the car. So, but those are the 5 levels. And now we're going to see some real videos of real cars, so you can distinguish between them. Okay, they are a bit long, 3 minutes each. with real. I decided to put this guy because he's quite funny, but it is showing really how it works. So you understand what is the difference between level 2 and level 4, because it is for me the problem is that Tesla, maybe not Tesla, well probably also, but I think it is the media who is making a lot of Tesla automatic autonomous driving, but they are not really autonomous, and he will explain very well. Okay.
I'm in a Tesla Model S. This is a Tesla Model S fitted with autonomous mode. Autonomous mode means that I can take my feet off the pedals and I can take my hands off the steering wheel. It only really works on the motorway. If I want to start the autonomous driving and if I don't want to be in control of the car anymore, what I first need to do is to pull this lever back, like so. And what that does is it takes control of the pedal inputs. So basically it's radar guided cruise control. So I don't need to worry about braking or accelerating. I can also increase the speed like that, 75, 80 miles an hour. So
this is the longitudinal control. So it can accelerate and brakes automatically.
If I take over steering inputs as I do now, then this lever gets pulled back twice. Doink, doink.
This is lateral control.
And there we go. Okay. The car has taken over steering. No feet, no hands.
He shouldn't be doing that. He should be with the hands on the wheel.
This is so weird. What this system's aim is to stop driver fatigue. So when you're on a motorway like I am now, you can just relax a little bit more. You don't need to be focused on the car in front so much. So when you do get to the kind of twisty B roads and the town driving, you're more fresh. And that's a good thing. I'm not actually doing a whole lot of anything, except talking to you, maintaining eye contact. That's weird. I'm not going to test myself. Now obviously this car is in its beta stage, so I have got Ethan in the back. So what I'm going to do is I'm going to talk to the camera behind me, and Ethan is going to be watching the road, aren't you? Okay.
So if some bad thing happen in the road, so he will have an accident, okay, because he's just relaxing too much.
So the system isn't completely flawless quite yet. You can tell I just can't stop but looking in front of me. The system does get quite confused with, oh, it feels so weird. I can't do it. I can't do it. Oh. Now, where stuff starts to get interesting is if I want to change lanes. So there is a car in my blind spot at the moment.
If you want to change lane, the car is not going to do it. He has to tell the car, indicate, and then touch the wheel. Otherwise, the car will not do it. So it is not autonomous deciding where to go and why. Okay?
If I don't hold the steering wheel, then the car won't move. And then I also need to cancel the indicator. And then you'll
so it is
lanes.
A good assistant to increase security, but it's not self-driving.
So at the moment I am on, twiddle this knob. So 3 car lengths, 2 car lengths.
You can adjust the distance with the obstacle. This is not a good idea. And this is
steering wheel.
This is something that has all the cars. This system is that eventually, if you have been relaxing for too much time, the car detects it and say, "Please hold the wheel, because I want to check if somebody is here." So it is. If you don't touch the wheel, it will automatically stop. Okay? It's a security system, but should be working more every less time. Okay? So, and here we have level 4. Level 4 is very different thing. This is just a prototype. Okay? It's not commercial one. Oh no, not this one, but this one.
One of the most advanced autonomous cars today is the mind-off Level 4 equipped Symbiotes, a vehicle that makes the Level 2 equipped Tesla suddenly look a bit like a horse and cart. What we're going to do now is going to go into full...
This guy there is only because, according to the law in France, there has to be someone in control of the car, but he's not touching. He's just ready to do it, but he's not touching.
Oh, I know you can let it go.
I can turn around now, right? Wow, I can literally just switch off and have a conversation with you guys. This is so much more than Tesla Autopilot, because with Tesla Autopilot that you saw about 2 or 3 years ago, is changing lane?
Yeah.
This changing the lane automatically. It is overtaking another car, and actually it is fixing the speed according to the limits, which is detected by cameras and by on the air. Okay, so the car is doing everything.
Having an autonomous car. Here in this level 4 car, you can pretty much do what you like. Ethan, tell me your thoughts.
It's absolutely ridiculous.
Yeah.
I think the distance you have to
trigger, yeah.
want to know as well.
Yeah.
This is just moving.
So how do I set my top speed, and how does it just
It's
stick to?
automatic, based on the road signs
Yep.
and based on the map.
So it will stick to 130 kilometers an hour, no higher. It's changing lane. The windscreen wipers, I presume, will go on, even though it doesn't really matter because I don't really need to worry too much about what's ahead of me, right? We have a toll coming up. You're not doing anything.
So it is even able to pass the control. The car
Really working hard.
doesn't have to do anything because this is a controlled environment. They have already made some. They have put antennas in all the only a few kilometers in a motorway in France.
Yeah.
Yeah.
Yeah. What you probably can't see at the moment is that on the highway itself there are antennae. So there's 5 antennae on here. So in the central reservation there are antennae, and they talk to the car.
I got the smartphone here. I can
So
do
the car is
Darius,
continuously monitored by the
and then
system,
once we can watch
and the car is fed continuously with information. Okay, always the traffic, limits,
I'm in the driver's seat.
etc.
How messed up is that? Look at that. This is so weird. But you know what? I feel completely at ease. Actually, I'm going to.
So you see the difference between before he was scared continuously to take his eyes from the road, and now he's very relaxed.
Would I be driving? Speak completely honestly.
This is the idea, okay,
What?
of level 3, level 4 cars.
Yeah.
The car will react quicker than you
It
think.
seems like
Yeah, actually, it evaluates the situation 10 times a second.
How many times do I evaluate a situation? One time every 10 seconds, yeah, maybe that's fair. So what you're saying again is that the car is better than me.
Better than all of us.
Okay, merci à tout.
And this is level 5. I'm going a bit slow, so maybe if you are short, I can finish in the second part, but we will see.
We still have 10 or 15 minutes, okay?
I will need more, but okay.
Okay.
And this is not working. Why? No, this is not working. Pity. Okay, maybe I will have time. No, this is on the internet. This is a online video. Okay, I will try to put it later once I finish. Okay, but this is a Google car, and it shows how it really goes. Of course, it goes very well. It is an advertising, so but you can see how it drives in urban environment, surrounded by almost everything: pedestrians, bicycles, cars, static objects, whatever, and it can deal with everything. Okay, very expensive car. So we will talk about now briefly about all the sensors which have made this possible. The most important ones, okay, that distinguish autonomous driving from normal cars, because of course all the cars they have a lot of sensors, swift, speed, accelerometers, whatever. But for autonomous driving, you need some specific sensors. Of course, this is the architecture of the system, very complicated. This is the perception area with localization. Then you have the monitoring and decision system, navigation, and of course connectivity, which is very important. This is more or less the distribution of the sensors that usually are in these autonomous vehicles. We have a radar, LiDAR, yes, LiDAR is here. Radar for adaptive cruise control, LiDAR for emergency braking, pedestrian detection, collision avoidance. We have more short-range radars around the car. Then we have back radars, back cameras, video cameras, and then we have ultrasound for short range. Okay, this is typical inside autonomous cars. This is from Tesla web. This is real scale of how it is. This is a car, okay, and the shadowed areas describe the range of different systems. So this is a car. This first one is ultrasound, more or less. Then we have radar, which is something like this. LiDAR, which should be something somewhere. You see, they are not showing LiDAR because Tesla doesn't have LiDAR. So without a LiDAR, you cannot be level 5 autonomous. Never. Okay? They decided not to use LiDAR. Firstly, probably because it is very expensive. So it will increase the price of the car and also the electronics. But we have here this all the areas, and as I told you, for example, if you were 25 kilometers per hour, if you are in a level 2 car, which is the car has to deal with whatever happens inside the circle within 3 seconds. Okay, so everything that happens in this circle, which is about to 20 something meters, the car has to deal with it. Okay, if you are 50 kilometers per hour, the car has to deal with everything that happens inside here, in case the driver is just not taking care of the road. And if you are 120 kilometers inside a motorway, this is everything. The car has to deal with everything inside here in 3 seconds, between 1 and 3 seconds. Okay, so you understand the amount of data and decisions that have to be taken in a very short time and in a very long space or spread space. So sensor, the first one is the leader. Those are the 3 main manufacturers. This one is electrodynamic. This one is it is static. It's not using mirrors rotating. It is I forgot the name. Those are the most important ones. This is how it works, more or less. I think you know it is like a radar, but with light, with photons. So it is measuring the time the photons take to achieve to one point and turn back. And it is making 3 with a lot of beams in vertical direction and in 360 using mirrors. Well, mirrors or static, which is semiconductors. I don't remember the name. Anyhow, it produces 3-dimensional maps extremely fast from even static and not reflecting objects. So this is what helps the system to see, okay, in real time. Many systems are using them. Of course, you were on Google, military devices, robots, etc. This is me. I've been in an interesting demonstration in my university given by people from the University of Cartagena. I was very proud to see and touch one of those. This is about 40,000 euros, and this is about 4,000 euros. But the price is decreasing very fast. Okay, so in a very short time, definitely those the other ones without the mirrors are much better. Sorry?
Time of flight.
Yeah, those measure time of flight using laser. Okay. The other ones without the mirrors using semiconductors instead of the mirrors.
Brass scanning.
No. The technology is the same, but it has a name. I will remember later. But those are much cheaper because there are no mechanical parts involved, and maintenance is much better. But this was the first one. This manufacturer, that's why I put it, the most famous. They developed actually the first leader system in 2005 DARPA Challenge system, if you remember. This one was just in the front, and that was the second one they developed to the 2007 DARPA Challenge. So they have been here for a long time. And this is how it works, more or less. Going too slow. How long do they have? So you see, they see in 3 dimensions. Okay. This is how the car is seen actually. Okay. This is 3 dimensions. You can check the distance of the object, and in 360. Okay, it is extremely fast. It works very well, and it is used everywhere now. So you will see the pedestrians, everything with a great detail. Now you can understand the amount of data the car has to process per second to take decisions. Okay, this is 360 imaging in real time, together with radar, together with ultrasound, together with connectivity, together with cameras. So it is lots of data. This is radar. Usually, this is the biggest manufacturer now. They are mounting Tesla and Mercedes cars. They were also in DARPA Challenge project vehicles. This is the front one. They usually work in this band, 76 to 77 gigahertz. There are versions for 24 or 30 gigahertz, but with less accuracy. The good thing is that there are less interference, and they are cheaper and smaller. But they are quite cheap. I mean, those $100,000 to $2,000 per each of them. They're radar, okay, not processing unit. It goes apart, but they are quite cheap. Then this was also Bosch radar was in 2007 DARPA vehicle. And then we have also cameras, also Bosch, again, one of the biggest manufacturers. They have conventional cameras, just to lane assistance, road sign recognition, vehicle detection, also stereo video cameras to measure distances, direction of the objects, and speed. So cameras are really important also. Video is very demanding signals for processing. So here you have an example of a Stixer representation. Is a sort of 3D imaging made with stereo cameras. Okay. Here you have how it detects non-reflecting objects and can detect the direction and the speed, and in color it is the distance. Okay. It can be also made in real time in roads and also in 3D environments in the streets. Okay. And you have also these systems which are conventional. I'm sure you know of them. For line detection, this is how the car detects the line, how it recognizes the signs in the road, and this one how it recognizes the signs in the street. So it is made in real time, okay, to feed the system to take decisions. And then the last one is ultrasound. Everybody knows what is ultrasound. Everybody is having ultrasound in the cars now, so it is all vehicles are using them, but it is very short range.
We can prolong the presentation.
We can prolong it.
Yes.
How long?
10 minutes.
10 minutes. Okay, I'll try to go fast. And I see some faces now already sleeping, but so everything works. It's a lot of sensors, lot of processing speed and everything. But there are things that cannot be solved with processing or with technology, with electronic sensing. Okay, there is a need for connectivity. It is impossible to have autonomous cars without connectivity, and nowadays connectivity is not real. Google cars and Uber cars are not using connectivity. Connectivity, I mean connecting cars between them, and cars with the infrastructure. And it is impossible to do it with it. I will show you some examples. This was the first accident of a Uber car. Google car. A few years ago. It was the car was here, it has an obstacle, something just here, and it was trying to get into the lane. So the car detected a gap, detected the speed of everything, and thought, okay, I can get in. But it was this was a camera from a bus, and the driver of a bus, once he saw a car getting in, he said, no way. So he pushed, and then he hit the car. Just because it was human, and he doesn't want nobody in his line because he was, I don't know, in a hurry. And this one is another example. I call it the grandpa driving mode. It was, you can see this, this also went viral on the internet. It is a driver who saw a Google car and started monitoring it, and the car was actually trying to get into the motorway. But because nobody was allowing him to get into the motorway, he couldn't. And he stayed trying again and again, and at the end, he just do another recalculation of the route, and then gets into the system again. Just because it was too gentle, and people is very, very bold, very cunning. So we will not allow anybody to get in unless he pushes us. And this happens with autonomous cars, okay? Because we don't know which car is autonomous or not. And this is what happened with Tesla, for example. It happens with all the cars. This is very usual. It happened many times. So almost all the accidents you see are because of this, because the blind spots, okay? So this is we will see now, this Tesla car, there is a normal car, they are driving quite fast, 80 kilometers per hour, I think. And suddenly the car which is here just moved because it has an obstacle. So Tesla car, even it has a radar and whatever, it is not able to stop in that amount of time. So in that short time, and it crashes, okay? So this is what happened with the last accident. This Tesla hit a fire car, okay? Because it was a caravan in front of the driver. The caravan just moved fast to avoid the truck, and the Tesla driver just hit the truck, okay? So this is a very short example, but you see what happens. So the car moves, and then the Tesla driver couldn't stop, okay? You think it is a lot of time to stop, but it is not, okay? Even for humans, it would be difficult. And why all this happened? Because vehicles weren't connected. Imagine all the vehicles have all these sensors and they are connected. So the front car can tell the second car that he has an obstacle and he is going to move. So the car which is behind can know in advance what is going to happen, okay? So that's why it is needed connectivity. But connectivity is already a reality. You just stop me whenever you think it is enough, okay? This is reality. So according to AT&T, 14 million vehicles were connected in the second quarter of 2017. Okay, 50% of the new mobile lines in United States belong to cars. 50%. Okay, and we are not talking about the Internet of Things. We are talking only about cars. 50% of the mobile lines in the mobile system come from cars. Chevrolet has estimated that they are dealing with, in 2016, with 4,000 terabytes of information connecting between their cars. Okay, between the cars and the and infrastructure, well, mostly Chevrolet infrastructure. Okay, just to tell them information. 90% of the new vehicles in USA will be equipped with cellular modems in 2025. Ford estimates that next year they will have 100% of them. In Europe, it is mandatory now. All cars sold now, they have to have an emergency call system. So all the cars have a mobile line. Okay. Audi Connect and Mercedes Me Connect, which are the last two releases in the market, they have a smart assistant. It's like a Siri, okay, or Google Assistant. So they connect with the cellular system to recognize your orders. Okay, so imagine how it is getting. And of course, it is a business. INRIX is collecting data from 300 million vehicles in 65 countries, and this data is later sold to third parties, okay, with information of traffic, speed, consumption, etc. So it is considered that in a few years, the data produced by the car will produce more revenue than the sale of the car itself, than the sale of the car. Okay. Also, this is very interesting. 15% of the cars to review in 2015 was due to software problems. You know, cars today, they have a lot of electronics and they have to be maintained. Okay, and many of the problems is just software updates. So all these 15% of the cars all this spend were made only because the car has to be updated. But once it has connectivity, you can do over-the-air updates. Okay, you don't have to go to the seller. You just connect to the system and download the new software. Okay, actually, Tesla Autopilot. I have nothing against Tesla. I love them, but it's just reality is reality. Okay, Tesla Autopilot. Actually, you buy the car with all the sensors, but you don't have autopilot working. You have to pay extra money to get the autopilot, and you can do it over the air. You stay at home, I want autopilot. So you download the autopilot, the license probably, and then you can have autopilot in the car. So they say that it will save having over-the-air updates of 35 billion euros in 2022. That's probably why telecommunications has started to become something very interesting, because Internet of Things and cars and all this. And now some examples for you to understand how interesting is this. This is real examples of real projects. This is some of my colleagues, I think they are aware of this, but anyhow. This is a tablet connected to this vehicle, which is seeing what the vehicle is seeing. This is a camera broadcasting information for this one, so he's watching what he's seeing. This is really important for platooning. For platooning, if we wouldn't have connectivity, it is the sensor for the car who has to be dealing continuously with the platooning. But if you have connectivity, it's much easier. Okay, the cars doesn't have to have so many sensors, so the cost of the cars will be much lower. Okay, this one, for example, this is actually broadcasting information to that one, so it can see through the car. So it is the see-through systems. Okay, another important thing is that usually maps gets obsolete very fast because works on the road, because the environment or the infrastructure is changing. But once you can upload to the cloud information from your environment from the sensors, the maps will generate at the moment, and you can download the new map. Okay. And finally, collaboration with the infrastructure, because signs they change with time, because maybe the sensors are not working properly, because sabotage of the signs. So it is good to have connectivity. It would be mandatory for level 3 and level 4 cars to have connectivity with the infrastructure. Okay, but we can go even further. You see this example. It is, I think it's Czech company. I'm not sure. I watched it on the internet and I found it amazing. It is a drone. They have on top of a cross. It was monitoring speed and what sort of vehicle is this, and it is broadcasting to the system. So you see that it is measuring the speed of every vehicle in real time, and it is telling which sort of vehicle it is, and also, of course, counting the number of vehicles. So imagine, maybe it doesn't have to be a drone, it can be a camera or a system in a post or whatever, but it is also releasing the amount of data that cars have to consider, because it is the system which is making the detection and making the decisions and then broadcasting to the rest of the cars. And this is a real project. Okay, you can find it on the internet. It's actually working. And then very fast, the two standards which are now more or less be used in cars is IEEE 802.11p, which is an evolution of 11a. It is for vehicle-to-vehicle and vehicle-to-infrastructure. And the other one is not conventional. It is cellular. Okay, cellular vehicle-to-vehicle and vehicle-to-infrastructure. The vehicle-to-infrastructure is already working. Okay, and vehicle-to-vehicle it is almost working. Okay, there are you can find prototypes now. They can work in decentralized and centralized mode, distributed mode. This is, for example, an example of what you can find. It is the difference between 4G and 5G. With the new release of 5G, I think I put it opposite. This is the next one, which is important. 5G, which is now going to be the new standard of cellular communications. You know, it is extremely fast. The latency is 1 milliseconds. The traffic is about 1 gigabyte per second. Okay, so the difference between 4G and 5G, the time that will take you to command the car to stop, with 5G it takes 2.8 centimeters, and with 4G it is 1.4 meters. So you see, quite important and quite different is going to be the thing once we have connectivity with these fast systems. And well, this is more or less all the vehicles now. We have to have a lot of communications. Okay, it's really important. Vehicles will be connected, but not only with cellular. Probably they will have many different sorts of communications. But the problem is, and I will finish with this. Okay, 2 minutes video. The problem is something like this.
It's not fun to have your 2-ton SUV's brakes hacked just as you're parking in front of a ditch.
Okay, hold on tight. Hold on. Oh.
That's what I've learned from Charlie Miller and Chris Balasek, a pair of hackers who have spent the last year developing a piece of software that can wirelessly sabotage this 2014 Jeep Cherokee.
It hasn't been altered in any way. There are no devices attached to it. But like many thousands of Jeeps around the world, it can be remotely hacked over the internet through a cellular connection to its entertainment system.
And it
will
is
allow someone to
coming
take
through
over
the radio.
steering,
Imagine once the car start having
brakes.
cellular, Bluetooth, or whatever.
Turn the fan on.
Everybody can get
Yeah,
to the
turn the
car.
fan on so you can even notice it.
Alright, something just turned on, all the fans and AC and stuff. I didn't do that.
The trick started small.
Oh my god. There's a picture of Charlie and Chris in tracksuits that just appeared on the dashboard.
But as I drove down the interstate, things started getting unpleasant and very loud.
Can't turn it down. The air conditioning is blasting, the music is blasting, and I can't see anything because of the windshield wiper fluid.
Okay, do it. Do it. Kill the engine. So we're killing the engine right now.
It says part sense. Actually, can't accelerate.
I stomped on the gas, but the Jeep slowed to a crawl.
It says 20 to 30 miles an hour.
So you see the potential
I turned on the
problems
hazard
that
lights, but I
can
was still
have.
stuck in the right lane with no shoulder to escape onto.
Guys, I'm stuck on the highway.
Charlie and Chris have only tested the full range of their attacks on a Jeep Cherokee. But they say that hundreds of thousands of late model Chrysler vehicles may be vulnerable to a feature called Uconnect, an internet-connected computer in the dashboard known as its head unit.
These cars, head units, expose a particular service that probably they didn't want to. It lets you do things like query it for information like the GPS or the VIN or all sorts of other things, but it also lets you just run commands. So you have to first break into the car remotely over the cell network and then move laterally if you want to do things like send CAN messages. And those are the messages that we can use to control things like steering or the windshield wipers or braking.
They plan to release a portion of their exploit code at the annual Black Hat Hacker Conference next month. They've also alerted Chrysler, which is issuing a security patch. But they say a lot more needs to be done to protect a new generation of cars that are increasingly connected to the internet and potentially hackable. You guys, after their stunt on the highway, Chris and Charlie still wanted to show me a couple of other tricks. Below a certain speed, they can control the Jeep steering as long as it's in reverse, pop its locks, mess with the speedometer, and, of course, disable the brakes.
Okay, hold on tight. Hold on.
You're not getting out of that. We're going to be doing some
So, more or less, this is what I wanted to tell you. It's not very deep technologically, besides the first part, of course. But I think that you now realize how demanding and how challenging is this. And it is only the beginning. You think that Google has made it, but they are far from it. Okay? Okay, this is it. That's all what I wanted to say. So, thank you very much.
Also, to remember.
Okay, thank you. Thank you. To remember or to forget?
It depends on you.
Thank you.
And maybe any questions?
Everything was clear.
Okay, so it's time to have a coffee. Okay, half of an hour. It's
Next
in
room.
room B.